So we've talked about transformations, so now we're going to talk about something called step functions. And step functions actually have a few names. I call them step functions, but they're also called greatest integer functions, or sometimes they're called floor functions. And we're going to talk about where that definition comes from, or exactly what that means. But first, I want to show you how they're denoted. So it's either x with the brackets, square brackets. Sometimes you might see it with double brackets, and sometimes they write that as, like they do a bracket with a line on the inside. So you might see it like that as well. Or sometimes it's a bracket with just the bottom part, almost like an L, but it's smaller because it's just the bracket. And this is what the parent function looks like. And so the parent function is like the most basic form of any function. So this is the parent function, and you do need to have this graphed clearly in your notes. So make sure you make this kind of a bigger sized graph in your notes. And notice that it looks like steps or stairs, which is why they call it a step function. And so basically how one more thing. Notice that it is a function because each time you go to draw a vertical line, so imagine that you were to draw a vertical line, say here, you might think, well, this fails the function test, but really it doesn't because there's a point at the top as a clothesline, so that actually is a point. But right here, this open circle is not an included value, so this actually does pass the vertical line test. And so the best way to understand what step functions mean, what I tend to think of in my head, is that they round down. So normally you think, like if it's 0.5 or above, like 5 or above rounds up, 4 below stays the same, but here we're just going to round down on everything. And I think it's going to make sense when I show you what I mean by that. Okay, so for instance, if I'm thinking about the number 3.1, when I evaluate the step value of that, or the greatest integer value of that, the greatest integer is 3. And that's because I'm just looking at this integer part. I don't care about the 0.1. This actually comes in handy a lot when we talk about real world problems. Like you think about how many people could attend something. Well, if you solve the problem and you get 3.8, you're not going to have 3.8 of a person attending something. So we say 3 is the answer. So the same thing is going to happen here. The greatest integer with 2.99999 is 2. Even though that rounds up to 3, when we talk about actual like whole numbers, that's 2. Okay, the negative is going to be a little weird to you because this is actually not -2, it's -3. Because again, remember we're rounding, it's almost like we're rounding down, right? The greatest integer for 4 is 4, and the greatest integer for -7 is -7. All right, so you might need to ask me a few questions about that tomorrow. We'll talk about that a little bit more, but make sure that you have all 5 of these examples and that you have a note to yourself that it's almost like you're doing, you're rounding down, or you're just thinking about the integer below the value that you're at. Okay, so trying just to make sense of that graphically, thinking about all of the points on this step. So if you think about the x values on this step, they are numbers that are between 1 and 2, but they don't include 2. So those would be numbers like 1, 1.1, 1.358, 1.7, 1.999, right? And if we think about the greatest integer for all of those, and we think about rounding them all down, which is just to kind of make sense of it, all of these round down to 1. The whole integer part of these values is just 1. And so notice the value of this step is 1 every time. And you could take any of those steps and see the same thing. Now notice, as soon as you get to the value of 2, right here, this step jumps automatically from 2 up to the next stair step because 2 equals 2, this next value. That's why there's an open circle right here, right? So let's talk about how to graph this with transformations. Okay, so when we talk about graphing with transformations, This is going to be very similar to what we've done so far with absolute value functions. So I'm still going to do the same thing. Anything in this transformational form, I'm going to give myself a fraction. In this case would be 1 over 1 and an ordered pair. Inside's opposite, outside's the same. Okay, so we're going to start where we would normally start. 1, 3. And the fraction tells me I should go up 1, over 1 to get to the next stair step. Now, these stair steps, so I can go backwards and complete this pattern to find all like the steps in this function. And the stair steps all look the same. So if you look back at your parent function, all the ones that we're going to do have a solid value on the left, and they extend and have an open value on the right. So now we're going to go through and just draw all the steps. All right, and for your notes, let's do one more. So the second one, pause if you need to, and go ahead and try to write the fraction in the ordered pair. Okay, so I got -2, goodness me, -2 over 1. And then 0, -4. So I'm going to start this by plotting a point at -4. And when we graph this, I should have picked some better numbers. We're going to go, if I had room, I would go down 2 and to the right 1. So to go the other way, I'm going to go up 2 and to the left 1. I'm going to keep that pattern going. And then my steps still do the same thing. They go open, over to the right. And on this, you can kind of see a little bit more what the vertical and horizontal is doing. So I'm going to zoom in and talk a little bit about those words that we learned today, those transformational words. So if we look at this example, let's zoom in. We said that this was vertical. Goodness me. This is vertical and this is horizontal, the -2 and the 1. So notice that vertically, that changes how tall the stairs are, right? How far apart they are in this vertical direction. And in each of those, the stairs are too tall. And this horizontal component, remember, we don't ever mess with that, but you can really see it in the step function. That's telling you how long this step is. Each of these steps is one horizontal length long, 1 unit in the horizontal direction. If these numbers were different, it would make the steps longer and maybe a different length apart. So I hope that you can see, and you might need to write that in words for yourself, that this is the height of between the steps, and the horizontal shows you the length of each step. All right, so we're going to do transformations with these tomorrow.